in Electrical Engineering from Federal Center for Technological Education of Minas Gerais in 2019. And currently she is a PhD student at the Federal University of Minas Gerais. In addition, she is a collaborating researcher at Gerência de Especialista em Sistemas Elétricos de Potência, where she develops works and research in the area of power electronics and power electrical systems, with research related to multifunctional modular multilevel converters. Please, the floor is yours.
Good morning to everyone. Good morning. My name is Renata de Souza. I'm a PhD student at Federal University of Minas Gerais. And today I will introduce you to the work titled as Thermal Stress Evaluation of Multifunctional Modular Multilevel Converter, STATCOM operating as active filter. Here's my agenda. First I will give you an introduction to the subject. After the methodology, case study, results, and conclusions. The electrical power system is a complex structure with a huge variety of loads. Most of these loads are non-resistive or fluctuating. These loads can produce non-unitary power factors, grid voltage variation, and power quality deterioration. These phenomena can produce also inefficient usage of the power and are the most reason of equipment failures. In order to solve the grid voltage variation, we have the reactive power compensator. So, nevertheless, in the literature, we have several reactive power compensator technologies. The STATCOM has been highlighted between among the other technologies. About the STATCOM, over the decades, several topologies also was implemented of STATCOM. One of the most interesting for medium and high voltage application are the cascade 8-bridge converter and the modular multilevel converter. The cascade 8-bridge converter, CHB, is commercially available. However, the modular multilevel converter, according to the literature, has presented superior results in terms of ambulance voltage conditions and negative sequence injection. So, in this work, we will consider that we will employ the MMC in our work. During a STATCOM operation, we have moments in which we do not use the full capacity of the converter, as you can see in one day here. So, in this moment, we can use the converter to do other works, ancillary service, in which we have the grid and then our MMC STATCOM, and a non-linear load, for example, in which we could compensate harmonic. We made harmonic compensation. So, in this work, we will study the use of an MMC STATCOM for also APF, active filter operation. So, we have a multifunctional modular multilevel converter, which will make active power compensation as in STATCOM operation, and harmonic current compensation as an active filter, power filter, APF. The MMC as active power filter has several works in the literature. Nevertheless, neither of these works study the thermal stress that the harmonic compensation can cause in the cell components of the MMC. So in this work, we will study the STATCOM, the thermal stress in the STATCOM operation and APF operation. The modular multilevel converter is composed by upper arm and a lower arm. Each arm is composed for n submodules and SEM. Each SEM is composed by a capacitor and 4 semiconductor devices, 2 IGBTs and 2 diodes. About the control strategy that we employ a circulant current control and a grid current control. the grid current control is composed for an outer loop of voltage and an inner loop of current. In the case when we are made the harmonic compensation, we put the reference, the current that we wanted to compensate right here, addicting to the grid current reference. Also, the outputs of these controls is the reference for our modulation strategy, which in this case is the next level control with cell tolerance band, the analyses CTB. In case, different of the case when we are using the MMC for STATCOM operation, in this case we have other frequencies, so the impedance of the system are different because we have another frequency different of the fundamental frequency. So we have to estimate the limitations of our converter for this operation. So we employ an interactive algorithm that finds the maximum harmonic current that can be synthesized by the MMC. In this case, we employ this algorithm for the 57 and 7 current harmonic current mitigation. These are the results, the limitation posed by the maximum voltage synthesized by the MMC in the injected harmonic current. So in our third case, we are considering MMC with a pole-to-pole DC voltage of 28 kilovolts, a rated power of 15 MVA, a grid power of 13.8 kilovolts, and a grid current of 60 Hz, and 18 SEMs per hour. This is our system in which we have the grid, the MMC STATCOM in parallel with a non-linear load. Also, we consider 4 cases of operation. The first one we have only STATCOM operation, and the others we have only APF operation. In the first here we have only 50 harmonic mitigation. The other we have only 70 harmonic mitigation. And the last one we have 50 and 7 harmonic mitigation. About the results first, in this dynamics we consider that in 0.5 we insert the non-linear load, and in 0.8 seconds we start to compensate the harmonic. So for the first result, the MMC output current, we can see in these details, which is after the compensator starts, that the converter, the MMC, produce the component, produce the current according to the frequency of the operation. In case of static operation, fundamental frequency, and the other the component of the frequency of the component, the harmonic component. In the case of our grid current, we can see in the details also for the after the harmonic compensation starts that the STATCOM presents load distortion in all the components in the current, and the THG is lower than 50% that is established for the standard. About the simple current, we can see that no expressive bit change was demonstrated, in which the STATCOM presents a higher ripple, maximum variation of this current, which is 40% higher than the others. So the ripple in APF operation is lower. Now, in the results of SEM capacitor volts, we can see that in the details, also for after the compensation starts, that the capacitor ripple is lower than in STATCOM operation, in APF operation in all cases. Also, we can see that we have a ripple in the components, which the component of the harmonic that we compensate is the lower component in this ripple. Also, this results show once the ripple is lower, that when we made the design of the STATCOM, which also will operate as an APF converter, that we will consider only the STATCOM condition, energy requirements for this case. About the thermostat on the semiconductor device, here we have the junction temperature of each device for all the case that we are studying. We can see that in STATCOM, we have the highest temperatures, and among the case of APF operation, the 50 harmonic current is the one that has the highest temperature. Also, we can see that in the case of APF operation, we have other cyclings in the temperature, which are a result of the harmonic component. In the thermostress of the capacitor, we also can see that the STATCOM has the highest temperatures, and the APF with 50 harmonic current compensation has the highest values of temperatures among the others of APF operations. About the conclusions, we can see that the results show lower circulating current people and SEM voltage people during APF operation. In the case of STATCOM operations, present the highest temperature for all cell components. Among the case of APF operation, the case of 50 harmonic compensation was the most stressed, and the results show that MMC STATCOM has potential for multifunctional operation. I would like to thank the institutions UFMG, Cefet, and UFV, and the financial support of CAPS, CNPq, FABEMIC, and the research groups Gesep and Gesep.
Thank you very much for a very interesting presentation. So we can open the floor for